inverses. Okay, but before that I would like to give you one application of multiplicative inverse that is commonly used in cryptography, and you might be aware of it as well. Okay, so RSA, RSA algorithm you have heard of. It is public key cryptography system. Okay, so in RSA algorithm we have a public key and a private key. Okay, so public key, as the name suggests, is public. Everybody can access the public key. Everybody knows the public key, right? And everybody knows the modulus n, right? So basically public key is denoted by E, right? And modulus is n. So basically everybody knows about E and n. And from this information we can calculate something called as the private key, which is denoted by D. Okay, now these keys are actually exponents. Okay, so whatever the message that you have, which is normally denoted by M, let's say, so M raised to E means you will encrypt it with the public key, and the private key will be able to decrypt this message. So for that, this key pair, that is public private key pair, should follow this property that ED is congruent to 1 mod psi of n. And this is called as torsion function, which we'll see later. But the key idea is it should follow, E and D should follow this. So to find D given E, you should be able to solve this equation. Okay. Now this is as good as finding the inverse of E. That is, D is the inverse of E mod psi of n. Okay. So this is the application of what we are studying now. It is the multiplicative inverse. So coming back to our terminology that we stopped here in the previous lecture basically. Okay, Ax is congruent to B mod M, that is Ax minus B is equal to Km. Instead of K I use some different alphabet, that is we use Y. So Ax minus B is equal to Ym, and then Ax minus My is equal to P. Now then we saw the definition of multiplicative inverse. So A and B are multiplicative inverses of each other mod M if AB is congruent to 1 mod M. Examples are 2 into 3, which is 6, is congruent to 1 mod M. Therefore, 2 and 3 are multiplicative inverses. And similarly, 8 and 7 are multiplicative inverses mod 11. Okay, now let's say in general, our problem statement is this, that we want to solve AX is congruent to 1 mod M. This X we want to find. We want to solve this for X. We want to find the inverse of A. We want to solve for X. Now, as you can see, okay, this inverse, multiplicative inverse X exists. Okay, inverse exists if and only if GCD of A and M is 1. Multiplicative inverse of A with respect to modulus M will exist if and only if GCD of A and M is 1. Alright. So let's try to find an inverse. Let's try one example. Okay. Let's say we want to find the inverse of 13 to mod of 100. Now, by brute force, what we'll have to do, we will have to check with 1, 2, 3, no, 13, whatever the result is, you will divide it by 100 and you will see if the result is 1 or not. Okay. So this is the brute force method which we will not be using. So what we'll be using is we'll use this result, or we'll use this uh, technique. So AX is congruent to B mod M. That means AX minus MY is equal to B, is equal to B. Okay. So same thing if I write here, then it will be 13x minus M is 100. So 100y is equal to 1. Now if you recall, when we had solved for the Euclidean algorithm, we had uh, we had expressed the GCD as the linear combination of the two numbers. So in this case, our two numbers are 13 and 100, that is A and M. That's why we said that inverse exists if and only if GCD is 1. Okay, because we want to find, there should be a 1 on the RHS, only then we can find the inverse. Okay, so let's apply the Euclidean and the extended Euclidean algorithm at the same time. Okay, so 100 is 7 into 13, which is 91 plus 9. Same time I'm building the table. In this table, 100, I'll write a different ink. This table, 100 x y 1 0. Okay, then 13 shift left and divide. Okay, so 13 shift left 9, correspondingly in the table 13 x is 0, y is 1. Okay, next row, next row is shift left 9 is equal to shift left again 4. So 2 4s are 8 plus 1. In this row, you will have 9 as the row. Now what will be the x and y? One and 7. Anyone else? Almost correct. It's almost correct. Just check the sign. Yes, 1 and minus 7. Okay. 1 1 and -7. Okay, and the logic behind this was 9 is equal to 100 minus 7 into 13. Okay, this we had seen that day. That is in the previous lecture or previous to previous. Okay, 9 is equal to 100 minus 7 into 13. So we say it in terms of rows. That is, the row of 9 is equal to row of 100 minus 7 times the row of 13. So row of 9 is row of 100, which is the first row, minus 7 times the row of 13. Okay. Okay. Then shift left 4 is equal to 4 into 1 plus 0, and it's over. Okay. Similarly, build a row for 4 here. 4 numbers. Are all of you getting this? How we are finding this? -1 and 8. Okay. And why? Because 4 is equal to the row of 13 minus the row of 9. Okay. So 0 minus 1 is -1, and 1 minus -7 is 8. Minus minus becomes plus. Okay. Then, but we want to find for 1. Okay. So we'll go one more step in the table. Okay. We'll go one more step in the table. See, in the Euclidean algorithm, we have achieved the goal. Our GCD is 1. Okay, Euclidean algorithm is over. In extended Euclidean algorithm, we still wait till we have a 1 over here. Okay, this one, okay, or this one you can say 1 over here, and 1 is equal to row of 9 minus twice the row of 4. Row of 9 minus twice the row of 4. So 1 minus -2 becomes plus, it is 3, and here we get minus 23. -7 minus 16 is 20, minus 23. Okay, so what we conclude from this is 1 is equal to 100. uh, yes, okay, 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 just focus on this part. Okay, we normally use, see, we wrote here that, okay, 100 with x and 13 with y. Okay, so finally our x is 3 and y is -23. Minus 23. How did it help us find the inverse? Basically, so 13 into -23 is congruent to 1 mod 100. 1 mod 100. Okay. Therefore, inverse of 13 is -23. Now, if you want to find an inverse, now inverse is not unique as such. Inverse is not unique. Okay. We are dividing by 100. So the inverse will repeat itself. Okay. So minus 23 plus k times 100, where k is any constant. They all will be inverses of 13. Okay. So if we want an inverse within the range of 0 to 100, a positive inverse if we want, then we can say that, okay, so these are all inverses. Okay. And we can say that minus 23 plus 100, which is 77. So 77 is also an inverse. And you can actually verify, you can calculate 13 into 77. Okay. So 13 uh, into 77 is congruent to 1 mod 100. Okay, so this is how extended Euclidean algorithm can be used to find the inverse. Okay, x and y should be switched in the equation. No, the aim was, see, I started with x over here because x, like x was the unknown, the inverse that I wanted to find. The only reason of bringing it in this form was because to make it familiar with the, or like because we had used a similar terminology in Euclidean algorithm when, you know, so that's why I used this over here. Yes, it should have been switched actually, I think. Because we are actually finding 100 plus 13y is equal to 1.
Hello, sir.
Yes.
Can you explain the last part?
This part minus 23, this part.
Yes, yes, sir.
Okay. So actually yesterday also it was the same thing, right? Uh, for example, okay, let's take smaller example. Okay, 8 into 7 is 1 mod 11. Okay, so 7 is the inverse of 8 mod 11. Now what I'm saying is, because the mod is 11, we are dividing it by 11. The same thing will happen at every multiple of 11 when you add a multiple of 11 to 7. So, and why this is, for example, like if I say 8 into 7 plus k times 11, it will always be congruent to 1 mod 11. It will always leave a remainder of 1 when divided by 11. So, okay, so 8 into 7 is 56. 8 into 18 is actually 8 into 7 plus 11. And you're dividing it by 11, right? So it is like dividing it by 11. So it will be 8 into 7 plus 8 into 11 divided by 11. Okay. So this part, 8 into 7 divided by 11 plus 8. Okay. Now this will not affect the remainder. Okay. So if you actually calculate 8 into 18, it is 64, 6, 144. Okay. And actually 143 is, the remainder is 1 again. Did this example make something clear? to you why we can do this?
Yes, sir.
Okay. So let's take one more example. And okay, so anyone else has any doubt?
Hello, sir. Sir,
Yes.
why did you subtract 23 from 100?
No, see, 23 minus 20. No, I did not subtract. Minus 23 is what we get from the extended Euclidean algorithm. Extended Euclidean algorithm gives us
Yes.
minus 23. Minus 23 is an inverse that we get from extended Euclidean algorithm. But this is also a perfect answer. Minus 23 is also an answer. It can also be a final answer. But if we want some positive number, let's say we want it between 0 and 100, any positive integer, let's say. Okay. So for to make it positive, I added 100. Okay. And the fact that because 100 is the modulus, adding 100 to it will not change the remainder. That's why I added 100 to make it positive as well as not change the remainder. Okay.
Okay, okay.
Okay. Sampath, your question is also solved with this. Yes. Okay. Uh, Actually, 13. See, x, y. These are just integers. Okay. If you stick with x and y, like we are changing it, we are. The idea is either you say 13x minus 100y equal to 1, or 100x minus 13y is equal to 1, or you say 13x plus 100y equal to 1, or 100x plus 13y equal to 1. The idea is that the GCD, that is 1 in this case, the GCD of 13 and 100 is 1. The GCD can be expressed as a linear combination of the two numbers, that is 13 and 100. Okay, then they are just numbers. Okay, you write it in any order. Yeah, the only idea of my writing this was that uh, ax is congruent to 1 mod m can be written as the linear combination of a and m, that is 13 and 100. Okay, that was the only reason of writing this. Actually, you will have to find in this way only. Okay, we always like we take the larger number, and this is the technique. Okay, can we take one more example? Yes, we are taking one. Let's take one more example, and let's take smaller numbers for this case. Let's say uh, okay, we want to find the inverse of 7 mod 19. So okay, 7 mod 19 is we want to find 7x is congruent to 1 mod 19. Now I won't write any equation or anything. We'll just start with the algorithm. The only idea is the two numbers are 7 and 19. Their GCD is 1. Okay, so that we all know beforehand, but we'll apply Euclidean algorithm as if we want to find the GCD of 7 and 19. So solve simultaneously and you can verify basically whatever I'm doing. So 19, Verify the numbers, huh? Okay. No one pointed out the fault here. What went wrong?
2 into 2 plus 1
Yeah,
for
yeah,
5.
yeah. So 5, okay, 5 is over, then we'll have 2. 2 is the row of 7 minus the row of 5 minus 1, and finally row of 1 will be row of 5 minus twice the row of 2 minus 8. Okay, so we can say 19 into 3 minus 19 threes are 57 minus 7 into 8. That is, okay, plus 7 into minus 8. Minus 7 into 8 is 1. So we found these numbers. What is our inverse then? Which one is our inverse? Yes, minus 8 is our inverse. So 7 into minus 8 is congruent to 1 mod 90. And if we want to convert it to something positive, then it will be 7 into 11 is congruent to 1 mod 19, where 19 fours are 76. Okay, both of them are correct. You can also stop at the negative one, it's fine. Okay, any questions, anyone? Okay, now there is another trick by which you can solve this. Just look at this, okay, without using any algorithm also it can be solved, but mostly I'll mention it in the question that you'll have to use the, see, such small numbers and such small examples don't occur in cryptography or anywhere, but I'm just showing this technique just for the sake of it, like just as an observation that you could find it in that way as well. Okay, this is not the preferred way. What I'm going to write, this is not the preferred way, but just an interesting thing I wanted to show. So there is no fixed way to know. So 7x mod 19 Okay, let it be. Fine. Okay, leave it. Because again, there will be questions that how did we find the numbers? So basically, there are some like by observation. Sometimes you can solve it. Really? Yeah, I'll show it, but don't ask me how did you I find the numbers. Okay, so multiply 7x with 21x is congruent to, because we multiplied by 3, we'll multiply it on both sides, so it will be 3 mod n. Okay, now because the modulus is 19, we can add 19 to both sides without affecting it. In particular, we can add 19 over here. Okay, so as I said before, like a is congruent to b mod m, so a and b leave the same remainder mod m. So by that principle, you can say 21x is congruent to 22 mod 19. Added 19 over here. Okay, now, okay, one more thing, one simplification I left out. Okay, so it is 21x. 21x, that is, there is a factor of 19 here already. Okay, it is 19x plus 2x, right? 19x plus 2x is congruent to 3 mod 19. So this part will not leave any remainder, right? This is divisible by 19. So this can be reduced as 2x is congruent to 3 mod 19. Okay, then we can add 19 to both sides, or not both sides, to 3 we can add 19, because the remainder will remain the same, 22 mod 19, and then we can divide by 2 on both sides, so it will be x is congruent to 11 mod 19. Okay, so we found the 11 in another way. If you understood this, it's okay, otherwise it's fine. Okay, the next thing is, now this is how we found the inverse. Now this can be done for, so this equation can be solved for non-zero numbers on the RH, numbers other than 1 on the RHS as well. So for example, uh, let's say we want to solve 7x. Instead of finding the inverse, now I want to solve for 7x is congruent to 4 mod 19. Now I already know the multiplicative inverse of 7 mod 19. So multiplying on both sides by 11, it will be 77x is congruent to 44 mod 19. Okay, and now this is actually 76x plus x, and this side is actually 38 plus 6 mod 19. Okay, so 76x will not add any remainder, because x is an integer and 76 is a multiple of 19. This will not add any remainder. That is, the remainder will be 0 for this component. Similarly, for this component, the remainder will be 0. So we can simplify this and write it as x is congruent to 6 mod 19. Okay, so 7 6 are 42. You can verify that x is 6. Did you get this calculation? Did you understand this? Okay. Now,
Hello, sir.
yes,
Sir, why did we ignore 76 and 38 at last?
because they are the multiples of 19. So the remainder will be as it is 0. Mod 19 means that we are dividing by, okay, when we said that A is congruent to B mod M, one of the definitions or the statement I made yesterday was that A and B leave the same remainder when divided by M. So we are dividing A and B by M. So if I divide 76x by M, that is 19, remainder will be 0. That's why only this component will cause the remainder that I kept and this I ignored. And similarly, yes, are you saying something?
Yes, sir, clear.
Okay, okay.
Excuse me, sir.
Yes,
So sorry, but I lost my internet connection. So can you just repeat after the 44 part, like how we got 38 plus 6?
that is by observation. So, like 19 is our modulus. Okay, like hope for it. Like uh, we know that. See, like before solving this, that before solving 7x is congruent to 4 mod 19, we first have to solve 7x is congruent to 1 mod 19. That is, we must know the inverse of 7. Okay. Now, why inverse of finding why finding inverse is important? Because uh, it will not affect the equation as such. Okay. Multiplying both sides by 11, which is the inverse of 7, we got 77x is 44 mod 19. Okay. And because the mod is 19, we tried to find a multiple of 19 which is closest to 44. In this case was 38. Similarly, we tried to find a multiple of 19 which was closest to 77, which is 76, and thus we got this. Okay.
Okay, sir.
Okay, let's solve one more example like this. Let's say 3x is congruent to 4 mod 26. Okay, now this is a simple. Okay, so no need to apply extended Euclidean algorithm. In this case, you can directly see. So what is the inverse of 3 with respect to mod 26? You can also directly, you know, inverse of 3 mod 26. Nine will be the yes, 9 is correct. 3 into 9 is 27, and 27 mod 26 is 1. So 9 is the inverse. Okay, I hope all of you got that. So 3 inverse is 9. So let's multiply by 9 on both sides. So 27x is congruent to 36 mod 26. And directly, what is the inverse or what is the solution? What is x? Simple example, x is 10. Yes, x is 10. Okay, this is 26x plus x, and this is 26 plus 10. Okay, so okay, so that brings us to something very interesting called as the Chinese remainder theorem. Okay. This part is clear, I hope. The next topic is Chinese remainder theorem. So there is a Chinese puzzle basically, which is, it may not be the exact puzzle, I don't know, but it is said that the original query or the question was find a number which leaves a remainder of 2, when divided by 3, and which leaves a remainder of 3 when divided by 5, and which leaves a remainder of 2 when divided by 7. Okay, same number when divided by 3 leaves a remainder of 2, when divided by 5 leaves a remainder of 3, and when divided by 7 leaves a remainder of 2. So these are the congruences that you will get. Okay, x leaves a remainder of 2 when divided by 3. Okay, you get these congruences. This is the puzzle or the kind of question that we want to solve. What is such number? Okay, so what is the simplest, or the brute force method of solving this? How will you solve this? So let's take any two of these. Okay, let's say I take x is congruent to 2 mod 3 and x is congruent to 3 mod 5. So start by make a list of numbers that leave a remainder of 3. So you can start from anyone. Okay, so let's say I start with this one. Okay, so what are the list of numbers? Preferably positive numbers. Let's start. So which leave a remainder of 3 when divided by 5. 3 is one of them. 8 is one of them. With a difference of 5, you will get it, right? 13 is one of them. 18. Get the point? This is the list. In this case, 2, then 5, then 8, then 11, and so on. So now if you see, 8 is common in these two. So 8 when divided by 3 leaves a remainder of 2, and when divided by 5 leaves a remainder of 3. Okay. So similarly, if we want to solve for 3 congruences at once, then we'll write 3 lists. Okay. In addition to these 2 lists, now we will also add the list of x is congruent to 2 mod 7. We'll write the list as 2, 9, 16, 23. This will go on for a while. 30, 37. Let's add to this list as well. 23. Okay. So the next number in the list is 23. In this case, 14, 17, 20, 23. Fine. So by matching the lists, we find that 23 is in all three of the lists. So therefore 23 is x. Okay. Now this method works, but what if the numbers are large? Instead of 3, 5, and 7, If you have some larger numbers, then it will take a lot of time. Okay, so the other technique to solve this is since x is congruent to 2 mod 3 means that x minus 2 is equal to 3t by definition of congruence. You get this? Okay, therefore x is equal to 2 plus 3t. Now what is this? So actually this is 2 plus 3t. If I substitute it here, 2 plus 3t is congruent to 3 mod 5. Okay, so what can we do? We can subtract 4. Sorry, we can subtract 2 from both sides. So 3t is congruent to 1 mod 5. Okay, so we'll introduce another t. So 3t minus 1 is equal to 5t1. 3t minus 1 is equal to 5t1. Okay, hold on to this. X minus 2 is 3t. Now we have 3t minus 1 is 5t1 after substituting into the second one. And now the third one is x is congruent to 2 mod 7. Uh, x is 2 plus 3t. It's congruent to 2 mod 7. Okay. What can you make out from this? 3t is congruent to 0 mod 7. So which actually means that 3t is a multiple of 7. Okay, so we can say that t is congruent to 0 mod 7. How does this help? Okay, so let's say, so let's substitute t equal to 7. Then in this case, okay, so we can directly find, so this wasn't any of any use over here. Okay, this was not required. just wanted to find x. So in this case, if t is 7, then x is 23 from this equation. Okay. So this is one way. Right?
Excuse me, sir.
Yes.
So the place where we got 3t is congruent to 1 mod 5.
Yeah.
Yeah. If we use the multiplicative inverse property here, so we can get the value of t na, if in case there's a situation where we have 1 there.
So you'll have to find a multiple of 3, which leaves the remainder of 1,
So 3 into 7 gives
3 into
21.
7.
So
So you could find it over here as well directly.
yes.
T as 7. But in this case, it was quite more apparent. Like, so subtract 2 from both sides and t is congruent to 0 mod 7. Actually, I was thinking that now can this be solved by uh like not only 23, okay, but if I substitute t equal to 40, that is another multiple of it. No, no, it doesn't work. Okay. So it can be that t equal to 7, if I substitute t equal to 7 here, and it also satisfies this equality. Okay, so I can, so this was not required actually. This was not required. Okay. So x minus 2 equal to 3t I got from the first one. From the second one, I got that 3t is congruent to 1 mod 5. I need not simplify it any further. Actually, if I simplify, this is not a wrong statement to say, but it is not of any use in solving for x, basically. And then we have this equation which directly gave us t is congruent to 0 mod 7. So we tried for t equal to 7 and it satisfies it over here as well. If it was for any other multiple, so if we say that, like, what about 14? 14 mod 7 is also 0, but it does not get satisfied over here because 14 3s are 42, mod 5 is 2. Okay, so it does not satisfy this equation. So 7 is the answer, basically. Okay, so that is another way of solving it. We substitute for the value of t. Yes. No, Chinese remainder theorem we were approaching. Okay. So the theorem is okay. The theorem is that if m and n are relatively prime. Relatively prime means GCD of m and n is 1. So if m and n are relatively prime, then x is congruent to a mod m and x is congruent to b mod n. Okay, has a unique solution mod mn. This is the theorem. Okay, and if we generalize this, and which is actually the Chinese remainder theorem, if we generalize this, what we get is, if in general, if M1, M2 up to Mr are positive integers and pairwise relatively prime. Pairwise relatively prime. What do you mean by pairwise relatively prime? Is GCD of Mi, any Mi, Mj, GCD of Mi, Mj is equal to 1 if I not equal to j. So if you pick any pair of integers from this, they will be relatively prime. Then the system of congruences, the entire system of congruences, x is congruent to a1 mod m1, x is congruent to a2 mod m2, up to x is congruent to ar mod mr, will have a unique solution, or has a unique solution mod m1 m2 up to mr. Okay, so the Chinese remainder theorem uh, helps in a way that, okay, what is the connection of the equivalence that we saw and this? We'll see. But for example, if you have an equivalence that x square is congruent to 1 mod 275, okay, then it is equivalent to saying, or instead of x square, just say it's x. Okay. That is not required over here. Okay. So it is the same as x is equivalent to 1 mod 25 and x is equivalent to 1 mod 11, which are the factors of 275. Okay. So how does it help in solving the problem that we had in hand? Okay. That we'll see. Okay. As it is, the time is almost up. This is the Chinese remainder theorem, and we'll see the applications of it in the next lecture. Okay, anything, any questions, anything you want to say? Okay, can you share these recordings? I'll see. I can share the whiteboards. Okay. Okay, thank you.